All right, boys and girls, welcome back to the drive-through for a little 5-minute lesson on conditional probability. Conditional probability is the likelihood that something will happen if something else has already occurred. One of the key aspects is knowing the notation. So the probability of A happening given B is true or B has happened will be written like this: the probability of A given B. Okay, so that's the first thing you have to understand is how to write it. Okay, so now this is the first most common way to do these questions. You'll be given an array, a set of data. Okay, and for these, all you have to do is add the data. In fact, in this one, they already did the addition for you. So you've got some data here in front of you. What's the probability that a member of the art club selected at random is a junior? So what do we know? Well, we know that we're selecting someone from the art club. We want to know what's the likelihood that that person's a junior. So this is going to be juniors on top that are in the art club, and then the total amount of people in the art club on the bottom. You just kind of got to read it carefully. So what's the total amount of people in the art club? It's 58. Well, how many of those people were juniors? 16. So we could reduce that fraction to 8/29. Okay. Now on the next slide, you're going to learn the formula. So you're going to want to put this formula in your notes. The probability of B given A is the probability that B and A will both happen over the probability of A. So if you look at how that applies to the previous chart, the probability that someone is a junior in art is 16 out of, junior and that they take art is 16 out of 115. So you have 115 juniors and 16 of them are in the art club. Now the probability that someone's in the art club is 58 out of 115, okay? And when you divide those two, it gets you back to 8/29. So we wouldn't have used this formula because we were given the information, but the formula still works, is all this is really showing you. This slide is telling you that if the probability of B given A is the same thing as the probability of B, well then these events must be independent. If the probability of B happening given A exists is just the same thing as the probability of B happening, then A has no effect on B and therefore they are independent. The second one is the converse. So that just says if you'd like to prove that something were independent, you can show that their conditional probabilities are equal to their actual probabilities. So now let's look at an example problem. So we're only given this data. We've got 70% of students plan to attend a concert and 30% do not plan to attend. So you can see these add up to 100. Now, of the 70% of students that plan to attend, 80% of them are fans of the band, okay? The other 20% might just be like coming along for the ride, or maybe they're working or something. So what is the probability that a surveyed student plans to attend the concert and is a fan of the group? Okay, so what's the probability that someone is a fan and plans to attend? Well, I know from our previous one that this is a conditional probability statement, okay? Now, we know that of the people that plan to attend, 80% of them are fans. So the probability that someone is a fan, given they plan to attend, here, let me write it down here, is 0.8. Okay. Now, we don't know the probability that someone is a fan and are going to attend, but we do know the probability that someone's going to attend. It's 0.7. So then to find our missing, you would multiply them, and that would give you 0.56. So that means that the probability that a surveyed student plans to attend and is a fan is 0.56. All right, I hope this helps.
Boom.